Welcome everyone to the Storage Sanitization session of the Compute Memory and Storage Summit. My name is Paul Suhler. I work for KIOXIA Corporation, where I'm an engineer working in SSD standards, and I'm also the chair of the IEEE Security and Storage Working Group. What I'd like to talk to you about today is eradicating data that has been recorded on a storage device. That technique is generally well understood, but doing it correctly can sometimes be elusive. Now, there's some new standards that are being developed. They build upon ISO 27040, which is storage security, and upon a standard from IEEE 2883, which was ratified 2 years ago. This is a standard for storage sanitization. These documents and the new ones to come will provide more clarity for organizations, as well as giving enhanced expectations of what is meant by reasonable security. Standards organizations we're seeing now are improving the coordination of their work. That will provide a more coherent set of standards, even though the standards are coming from these different organizations. I'll talk about that later. And finally, this session is going to talk about generally the framework of standards and the new capabilities that have recently come out and ongoing developments. So onward. The learning objectives that I hope you'll be able to take away are to understand new developments in data sanitization and related standards, understand which standards are of use to your organization, and finally, which standards bodies are addressing different aspects of sanitization. Now, as we go through this talk, please put your questions into the chat, and we will be able to address those later. So here's what I'm going to be talking about today. First, I'll give a vocabulary around sanitization so that you'll understand the terms that I'll be using throughout this talk. I'll talk about some of the new capabilities that have recently been approved. I'll talk about work that is still in progress that you should be seeing results of over the next year or two. I'll give an overview of the standards environment. Who are the different players, and to some degree, how do their different standards relate? I'll summarize what I've said and then finally issue a call to action for you to get involved. So here's the vocabulary. There are a number of different things that apply to sanitization. First of all, there are methods of performing sanitization, and these are defined in IEEE Standard 2883. The simplest is clear. The only requirement there is that after a clear sanitization, user data cannot be recovered from the device. Purge is the next level up. In this case, the device still remains usable after sanitization. The user data, again, can't be recovered from the media. Not just not readable, but it can't be recovered from the media, even if the device were to be disassembled and the media read at a very low level. Finally, the most thorough way of sanitizing a device is to destroy it. Destruct means that the device is completely destroyed, the media is destroyed, and the data cannot be recovered from the remains of the media. What I'm going to focus on for purposes of this talk is the purge method, in which all the user data in the storage device is eradicated, and the device remains usable again. Now, this has to include data that's stored in caches. For example, NVMe has a controller memory buffer, or persistent memory region. Those are separate buffers, non-persistent and persistent, and data, user data, may be in those, and it has to be removed as well. There are three techniques. They're called cryptographic erase, block erase, and overriding. I'll talk about those in a minute. One important aspect of sanitization is that the device can't be read or written, essentially can't be returned to normal use until sanitization succeeds. Why is that a requirement? The problem is that if sanitization fails, it may leave some of the data still usable. And if the person who is overseeing the sanitization misses the fact that it failed, they might send it off to be reused, exposing that user data to exposure, which can have serious financial consequences. So for that reason, only after sanitization succeeds will normal reads and writes be allowed again. What to do if sanitization fails? Well, in that case, the organization may require destruction, for example, shredding. Finally, one aspect is documentation of sanitization. It should be required, often it is, and the purpose of that is so that the owner of the device can ensure that sanitization was performed and that they can prove to outside parties that it was performed. Oh, I mentioned the encryption methods. Let's go back and talk a little bit more about that. The first method is overwrite. In this case, user data is replaced with a specified pattern. Now, this applies mainly to hard disk drives. Frequently, overwrite is done in multiple passes, and for magnetic recording media, overwriting locations multiple times is not really a problem. However, that is a problem with solid-state drives, which have a limited number of writes in their media life cycle. More appropriate for SSDs are block erase. This is an atomic erasure of each portion of the media, perhaps one plane of a chip at a time. Like I said, this applies to SSDs. It can be fairly lengthy depending upon how many areas can be erased at one time and how large the device is. The fastest mechanism uses cryptographic erasure. In this case, user data is encrypted as it is written to the media, and erasure simply means eradicating the key that was used to perform that encryption. This method, of course, can apply to all devices. And I reiterate, this is the fastest method of performing sanitization. So now let's look at some of the new capabilities that have come out over the last year or so. The first is a technique called key per IO. The purpose of this is to perform encryption at a fine granularity. For example, you may receive an order to purge the data pertaining to one person out of many people whose data is on a single device. The solution to this is that a file that belongs to one person will be encrypted using a unique media encryption key. Files belonging to other people will be encrypted using different keys. So NVMe has defined a way of doing this. Each write command can specify a different key for which to encrypt the data. And similarly, read commands would specify that same key to read the same data. Keys are not kept on the device, though. They are kept in a key management appliance. Inside the device, they're ephemeral. For example, on a power failure, or power cycle, I should say, the keys will be forgotten and would have to be reloaded. This means that if someone steals the device, they would essentially have to disconnect it and it would lose power. Then the keys are gone and they would not be able to decrypt the data on that device. Now, what happens once you've encrypted the data with different keys for different people's data? If the device owner receives an order to forget that person's data, then that person's key is deleted from the key management appliance. And at that point, the encrypted data can no longer be recovered from any storage device to which it was written using that key. Some of the standards that have defined this in NVM Express Technical Proposal 4055 is the one that allows each IO command to encrypt or decrypt with a different key. How do you get the keys into the device? Well, that falls to a Trusted Computing Group security subsystem class, also called key per IO. That explains the mechanisms for provisioning a storage device with the keys that are needed. There are more details that people have to go into when they are making use of key per IO. For one thing, how will you prove that all copies of the key have been purged from all of the key management appliances? In terms of implementation, if the entire device is going to be sanitized, then, for example, it'll have to be built with a mechanism that allows cryptographic erase over everything all at one time, perhaps a second level key that could be changed. You don't want to have to one by one delete all of the keys on that device. Okay, new capabilities. Another one is verification of sanitization. So the goal is to be able to prove that the original user data is gone. In other words, read the device to show it no longer contains that original user data. There are some problems with cryptographic erase and block erase because when those are performed, they invalidate the error correction codes on the media, and a normal read command will fail when it tries to read those. So verification can't be performed with the pre-existing read command. Recently, NVM Express ratified Technical Proposal 4152, which is called Post-Sanitized Media Verification. What happens here, after successful sanitization, the device will enter a particular state called media verification state. The read command in the NVM command set that applies to namespaces that use logical blocks. The read command will allow returning data despite the ECC errors, so that you'll be able to see the data that is on the media and know that it is not what was originally written. Now, the media manufacturers pointed out a problem that if a person with their device will repeatedly perform this read on the same locations, if they do enough reads, they can derive the media reliability characteristics, for example, the uncorrected bit error rate. Uncorrected bit error rates are extremely proprietary and no one wants those to be disclosed. So this TP 4152 allows the read command in the media verification state to return different data on successive reads, and that will obscure the uncorrected bit error rate because the reader will never get the same data twice. Finally, upon exiting the media verification state, all the media will be deallocated so that there will be no logical block addresses that can be read. So those are a couple of the recent completed directions in sanitization. There's still some work in progress. One is sanitizing a subcomponent of a storage device, for example, an NVMe namespace. One storage device can be shared by multiple virtual machines, each one running a different user, and each virtual machine is assigned a different namespace. So when one user is swapped out while the others continue to work, that namespace has to be sanitized. Other namespaces at the same time have to continue to be written and read. There are some other parts of the storage device that must not be sanitized, and this is a change from the sanitization of the entire device. For example, a controller memory buffer can contain a data buffer that may be used for IOs that are going to other namespaces. So any data in there cannot be touched. The only method of sanitization that really works for this is cryptographic erase. That way, the encrypted data in one namespace can be removed, and that even if that user data is intermixed in different parts of the storage device, intermixed with data from other namespaces, only the targeted user data is going to be erased. There's some other work in progress on the standards front. Two of these are in the IEEE Security and Storage Working Group. Project 2883.1 is called Recommended Practice for Use of Storage Sanitization Methods. It gives guidance basically on how to use standard 2883. This helps organizations understand what are the appropriate methods given their data. What are the risks, the feasibility, the effectiveness, the economics, and the environmental consequences of sanitization of those devices. This project standard is going to enter public review later this year. There's another one that is not directly related to sanitization, but indirectly related. IEEE 1619 has for many years defined cryptographic protection of data on block-oriented storage devices. This is the encryption method that is used on most self-encrypting drives. It defines the XTS AES block cipher. That's based on the advanced encryption standard. A new revision of this is in the works. It's going to tighten the key use requirements to improve security. In other words, reduce the number of bytes that can be encrypted with a given key to provide less data that could be used to crack the encryption. It's going to be entering public review this summer, if not sooner. Now, related to this is from the National Institute of Science and Technology. They will be updating their SP 800-38E, which gives guidance on the use of 1619, to refer to this new revision. So this is one of the examples I mentioned of different standards groups beginning to cooperate with one another and to coordinate their standards. More work in progress, again, in IEEE SysWig. One is a recommended practice for virtualized and cloud storage sanitization, 2883.2. This gives guidance on implementing sanitization for large-scale systems. IEEE P3406 is called Purge and Destruct Sanitization Framework. This provides requirements for defining new sanitization commands. It will define what parts of the device need to be sanitized, what sanitization methods are appropriate for the device, and finally, what are the means of verifying sanitization that should be included in the definition of those sanitization. We hope that this will be adopted by different organizations other than NVM Express that define sanitization for their devices. Additional work in progress. One thing that drives a lot of this is that customers have to be able to trust sanitization because, for example, the liability for a data breach can be tens of millions of dollars. If they don't have confidence that a storage device was sanitized, that maybe there were bugs or simply the method was ineffective, the customer may decide simply to destroy the device, which is a waste. One way of approaching that we're exploring is compliance testing. In other words, confirm that the device performs sanitization correctly. We're looking at potentially establishing a media sanitization certification program. At the moment, sanitization certification is done ad hoc by a couple of different third parties. They set their own standards for what they're looking for, and we think it might be an improvement to move these into a standard sanitization program. Finally, is circularity and reuse. I mentioned before that it's wasteful to destroy a device. You don't want to have to replace the device, and you don't want to pollute landfills with the detritus of destroyed devices. Ideally, we would purge user data and then reuse the device. Or if something goes wrong with purging, then destroy the device by disassembling it and recycle its components into different recycling streams, therefore reducing potential pollution. A little bit now about the standards environment. I've mentioned IEEE Security and Storage Working Group and the standards they work on. ISO IEC 27040 was recently approved in its second edition, and it interlocks with IEEE 2883. It relies upon 2883. The National Institute of Science and Technology provides many standards. They have the Cryptographic Module Verification Program defined by FIPS 140-3. There are testing labs that perform the certification, and they have many different special publications. They address different aspects of cryptography and security. And finally, the European Union has a regulation, 2019-424, often called Lot 9, and that can now refer to 27040 and 2883 together. So to summarize, some of the new developments are providing ways to sanitize portions of a storage device, to verify that sanitization took place, providing guidance for users and implementers, and coordinating the standards for sanitization. And most importantly, building customer confidence in sanitization. So, call to action. Please understand your organization's needs and perform sanitization accordingly. Consider using some of these new capabilities and participate in different groups that define different aspects of sanitization. Finally, take a moment to rate this session because your feedback is important to us. So thank you very much.